Hello, in this video we're going to cover Kirchhoff voltage law, Kirchhoff current law, and a little bit of resistors in series and resistors in parallel. In this first example we have one source with 35 volts, then we have one resistor R1 with a value of 1 kilo ohm, and then we have another resistor R2 and we don't know the value of R2. Now, something we know from this circuit is we have a total current I flowing here, and this current has a value of 0.01 amps. And we also know that the power dissipated by R2 is 0.25 watt. We are interested in finding the voltage across R1, the voltage across R2, the value of R2, the power provided by the source to the circuit, the power dissipated by R1 as well. So we're going to start here with the voltage. It's the easiest quantity we can find here because we know we have an R1 with a value of 1K, and we know we have a current flowing there that is 0.01 amp. So, applying Ohm's law to R1, we can get VR1. That is the voltage across the terminals of R1. So we take the voltage VR1 is going to be equal to the current I times R1, and this value is going to be 0.01 times R1, which is 1K, and we get 10 volts. Now, so we have 10 volts being dropped across R1, and we want now to find the voltage across R2, and that voltage is this one here, the voltage across the terminals of R2. So one way of doing this is by applying Kirchhoff voltage law, KVL. What we do here is we say, well, we have 35 volts, that's the total gain provided, that's the voltage provided by the source, and that has to be equal to the summation of the drops, VR1 plus VR2. So from there we say 35 minus the voltage drop across R1 has to give us the voltage drop across R2, and that is 25 volts. So we have 25 volts across R2. For the value of R2, well, we can apply Ohm's law because we know the voltage across R2 and we know the current flowing through R2. It's the same current flowing through R1 since they are both in series. So we can apply Ohm's law here and we get VR2 is equal to 25 volts, and that has to be equal to the current I times R2. And from here we get R2 is equal to 25, it's the voltage, sorry, divided by the current, and we get 2.5 kilo ohm. Now we want to find the power dissipated by R1, and that is simply the voltage of R1, VR1 times the current. So we get 0.1 watt. For the power provided by the source, we just take Vs and multiply it by the current, where Vs is the voltage across the terminals of the source, and in this example is just 35 volts. So we multiply 35 times the current that is flowing in the circuit, in this case 0.01 amp, and we get 0.35 watt. Something to mention here is we can check this result with the fact that the power provided by the source has to be equal to the summation of all the power dissipated in the circuit. In this case we have 0.1 watt being dissipated by R1, 0.1 watt there, and we have 0.25 watt being dissipated by R2. So the summation of those two is 0.35, which is exactly equal to the total power provided by the circuit. Now in this new example we have three resistors. R1 and R2 are in parallel, and then we have a third resistor R3 with 8 ohms, and the source is providing 2 volts. We want to know the current I, the total current I, and each individual current flowing through R1 and R2, and the voltage across R3 too. In order to find the current, we can simplify the circuit first, and we do that then by recognizing the fact that R1 and R2 are in parallel. So we can just draw an equivalent circuit. So we get R1 and R2 are in parallel, so we can compute an equivalent resistance. So we have here the source with 2 volts, R3, it's there, R3 is 8 ohms, and then we replace R1 and R2 in parallel with their equivalent, that I'm going to call R equivalent 1, and we can use here the formula for resistors in parallel. So we have R1 is 40 ohms and R2 is 10 ohms. So from there we get the equivalent resistance. In this case we get 8 ohms. Now we see that R3 is in series with this R equivalent 1. So we can simplify the circuit a little bit more just to get one resistor. So the total equivalent resistance here is given by R3, which is 8 ohms, plus the equivalent 1, which is 8 ohms too. So we get 16 ohms is the total equivalent resistance of the circuit. And we have the same current capital I flowing here and the same current capital I flowing in the equivalent circuit. So now we can apply Ohm's law to the equivalent circuit. We have just one source, one resistor, and we can easily find the current. So we get I has to be equal to, so we get I has to be equal to, so we get I has to be equal to 2 volts divided by 16 ohms. And we get 0.125 amps. And we have 0.125 amps flowing there, and 0.125 amps flowing in this other equivalent circuit, and we have 0.125 amps flowing in the original circuit with the 3 resistors. So that's the total current flowing in the circuit. Now we're interested in finding each individual current IR1 and IR2. This current I here will reach this node, and part of the charges are going to flow through R1 and the rest is going to flow through R2. We want to find each individual current. So one way of finding IR1 and IR2 could be to find the voltages. VR1 and VR2. VR1 is the voltage across R1 and VR2 is the voltage across R2. Now they're both in parallel, so that means the voltage drop across them is the same. And if we can find that voltage, then we can easily apply Ohm's law, because we know the value of each resistor, to get each individual current.
So the idea is to find VR1.
So we have here, let's try to find that voltage VR1. We have a current of 0.125 amps flowing through R3. R3 has a value of 8 ohms. So we can find the value of VR3. And now this voltage VR1 is the voltage across R1 here, and VR2 is the voltage across R2. Now they're both in parallel, so they're both the same value. So I'm gonna call this, I'm gonna say VR1 is gonna be equal to VR2, and this is gonna be equal to some V, and they are the same. We can see this in this equivalent circuit. The same voltage across R1 and R2 is the same voltage across the equivalent resistance that we have here. We have a total resistor here, or we have two resistors in series with 8 ohms and 8 ohms. Now we can find VR3 just by taking the current and multiplying by R3, and this is going to give us 1 volt. And now using Kirchhoff's voltage law, since we know that the source is providing 2 volts and we already have 1 volt being dropped across R3, so we have 2 volts is the voltage provided by the source, and we have 1 volt being dropped across R3. Therefore, we have to have 1 volt across R equivalent 1, which basically means V is equal to 1 volt. And that is exactly the same as VR1 and VR2. So now we can apply Ohm's law to get IR1, because we know VR1 and we know R1. And we can do the same for R2. We have VR2 and we have R2. For IR1 we have 1 over 40, and that's going to give us 0.025 amps. And for IR2 we have 0.1 amp. Now we can check this result with Kirchhoff's current law. We know that the total current I has to be equal to the summation of IR1 plus IR2. And in this case we have a total current I that is 0.125 amps, 0.025 flowing through R1 and 0.1 flowing through R2. So the summation is 0.125. Now in this third example we have 3 resistors in series. We know the value of 2 of them, we don't know the value of the third one, and we want to know the current, the voltage provided by the source, and the voltage drop across R2 and R3. We know the voltage drop across R1, in this case is 3 volts, and we have here 1 current I flowing in the circuit. And we also know the power dissipated by R3. So one way to find the total current in the circuit is by applying Ohm's law, since we know the voltage across R1 and we know the value of R1. So in this case we get 1 milliamp flowing in this circuit. Now we want to know the value of R3. We can use the fact that we know the power dissipated by R3. In this case PR3 is 2.5 milliwatts. And we can find this power in terms of the current I squared times R3. So from here we can get the value of R3. In this case we're going to get 2.5 kilo ohms. So the power PR3 is 2.5 milliwatt, and the total current is 1 milliamp, in this case 1 milliamp square, and we get 2.5 kilo ohms. Now in order to find the voltage provided by the source, well, we have here now 2.5 kilo ohms. So we know the value of the 3 resistors now. We want to know the voltage provided by the source, Vs. So one thing we could do to find Vs is to simplify the circuit to have just one equivalent resistance. Since we know the value of R1, R2, and R3, and we know the 3 are connected in series. So we can just simplify the circuit to have one source providing Vs, and then one equivalent resistance, and this resistance is going to be given by R1 plus R2 plus R3, since they're all in series. And the result is going to give us here 6 kilo ohms. So now we have here the same current I, 1 milliamp, that we calculated before. So we can apply Ohm's law here to get Vs, since we know the current and we know the equivalent resistance. So this is going to be 1 milliamp times 6 volts, seems 6 kilo ohms, so we get 6 volts. Now we want to find the voltage across R2 and the voltage across R3. We can easily do that because we know the current and we know the value of each individual resistor, so we can just apply Ohm's law. So for VR2 we take the current we multiply by R2 and we get 0.5 volts. And for VR3, we take the same current. They're all in series, so it's the same current for the three. And multiply by R3, so we get 2.5 volts. One way to check this result is using Kirchhoff voltage law. So we have a drop here of 0.5 volts across R2 and a voltage drop of 2.5 volts across R3. So as you can see, 2.5 plus 0.5 plus 3 has to give us Vs, which is the voltage gain in the circuit, 6 volts. We check the result with Kirchhoff voltage law.